Welcome back to the LTE air interface training. Now let's have a look at the principles of orthogonal frequency division multiplex. The principle of OFDM is the same in the downlink and the uplink. There is one minor variation. In the downlink, we are using the pure orthogonal frequency division multiple access. In the uplink, a slight modification, which is called single carrier frequency division multiple access. But the principle is basically the same. So now in the following, let's focus on the signal processing in the downlink. So first let's compare orthogonal frequency division multiplex with frequency or conventional frequency division multiplex. Frequency division multiplex is used, for example, in GSM. So we have the different GSM carriers, and we have a spacing between the frequency carriers, which is 200 kilohertz. But if one cell uses, for example, this frequency carrier, in the same cell we cannot use the adjacent frequency carrier because of the interference. This means the two frequencies are not orthogonal to each other, causing interference. It's different if we use orthogonal frequency division multiplexing. This principle is very old, about 50 years old, but at that time there was no technology to make this, to produce OFDM signals. Now we have fast signal processors, so it's very easy to produce OFDM signals. At the heart of the OFDM signal are the so-called subcarriers, which are very narrow band. One subcarrier has a bandwidth of only 15 kilohertz. This is very small compared, for example, to a GSM carrier, which has 200 kilohertz. And the spacing between these subcarriers is also 15 kilohertz. And the signal structure is such that the maximum of one subcarrier lies on the nulls of the adjacent carriers of all other carriers. So this means we have a perfect orthogonality, so that neighboring subcarriers do not interfere at all. It's only when signals from different base stations, which are not synchronized, are overlapping. In this case, we can have an interference, and this is the reason that we have a frequency spacing between the LTE carriers of different operators, for example. To produce the OFDM signal, we have different steps. First of all, we have to put the information bits on the different subcarriers. So we have a serial to parallel conversion So from a stream of bits, we put the first bit on the first subcarrier, the second bit on the second carrier, and so on. And in the so-called inverse fast Fourier transformation, we produce the different subcarriers modulated with the different input information bits. So the inverse fast Fourier transformation has a frequency as an input, and the output is a time-varying signal. This is the signal which is finally amplified by a radio frequency amplifier and transmitted via the antenna. At the receiver, we have the inverse process. So first of all, we have to amplify the signal, and then we have the fast Fourier transform, which produces the signal in the frequency domain from the signal in the time domain. And then finally, we make a parallel to serial conversion and get back the bit stream which was transmitted. So to summarize, OFDM can be visualized in the time frequency diagram. We have the different subcarriers in the frequency domain. In this case are shown 12 subcarriers with a spacing of 15 kilohertz. So 12 carriers together have a bandwidth of 180 kilohertz. And this is the smallest amount of bandwidth which can be allocated to one user. And then in the time frame, we have a time pattern. So signals for one user are only transmitted during 1 millisecond, and in the next millisecond, the allocation of the resources can be completely different. If we have a look at the time variation of the amplitude of one OFDM signal, that depends very much on the information bits or information symbols which are transmitted. So the amplitude variation of the OFDM signal is very high. And we measure this variation as peak to average power ratio. And for an OFDM signal in LTE, this ratio is about 10 dBs. This is a major challenge for the transmitter, and this is the reason why it was chosen to use a slightly different transmission scheme in the uplink compared to the downlink. In the uplink, we are using single carrier frequency division, multiple access, which generates a signal with a smaller peak to average power ratio. So we can use transmitters which have lower power consumption. And this is important for the headsets. An advantage of OFDM signals is related to the time domain interference. This shows a typical mobile phone signal at the receiver that is transmitted on different radio passes. For example, the signal with a high amplitude takes the direct transmission path from the source to the target, and the other signals are reflected signals which arrive later and with a lower amplitude. So this leads to a distortion of the signal, and in GSM we have to use a training sequence and equalizers to reconstruct the original signal. Another important point is the inter-symbol interference, which is shown here. If there is a big delay spread of the signal, then it can happen that the first signal, the delayed first signal, overlaps with the time slot of the second symbol, and then this generates an interference of the second symbol. The inter-symbol interference can be avoided by adding the so-called cyclic prefix. So in GSM we had the training sequence, and in LTE we use instead the cyclic prefix. The cyclic prefix is simply a repetition of the first part of the symbol. This is copied to the end of the symbol, repeating just the first part. And this helps, and if the delay lies within the length of the cyclic prefix, the delayed signal adds useful power, received power, to the received signal. Only if the delay is higher than the length of the cyclic prefix, we have an inter-symbol interference. So in most cases, we can use the delayed signal as a useful signal. So now let's summarize the first chapter. We have seen that LTE is a fourth generation mobile system. It was defined by 3GPP, which already developed UMTS. The principal technology which is used by LTE is OFDMA. LTE can be operated in two duplex modes, in FDD mode and TDD mode. It has a flexible bandwidth usage, and it can be operated in many different frequency bands. Thank you for watching.